Next, we're going to graph logarithmic functions. So let's try to answer the first question we posed to you in this section, again, but this time using logs. Now that we have the notation down of a log, we want to now be able to find the inverse of f of x equals 2 to the x algebraically. Going back to our steps, my first step was take f of x and make it into a y, just so it's easier to manipulate. Then I take my x's and my y's and I interchange them. That's my inverse step, when I interchange the x's and the y's. Step 3, I'm going to solve for the new y. And lastly, I take the y and turn it into f inverse of x. So let's look at our function. F of x equals 2 to the x. Instead of f of x, I'm going to write y equals 2 to the x. Next, I'm going to interchange x and y. So the x goes where the y is, and the y goes wherever the x was. This third step was the step we had a hard time with this section, solving for y, because I have the y stuck up here in the exponent, and we hadn't learned that until today. Now we know how to take a y out of the exponent, and the way we do that is to take this exponential form of the equation and change it into a logarithmic form of the same equation, an equivalent form. So I have log base 2. Notice the x and the y are switching sides, so the x is going to be with the 2 and the y is going to be on the other side. You can put the y in the back, or you could put the y in the front. It really doesn't matter to me where you put the y. And the last step is to take y and replace y with f inverse of x. It's not the same function that we originally started with, it's its inverse. So we use the f inverse, or f to the -1. It's not really a -1 power, it's called f inverse of x equals log base 2 of x. So f of x equals 2 to the x and f inverse of x equals log base 2 of x are inverses. And more generally, instead of using the 2 here as the base, what if I used a b for the base, meaning b could be anything? What would be the inverse of the exponential equation, b to the x? We have the logarithmic equation, log base b of x. So these are truly inverses. We've been talking about the opposite of exponential is log and the opposite of log is exponential, but now we have shown you algebraically that they are inverses. So let's practice finding the inverses very quickly. If I give you f of x equals 3 to the x, I want you to know that f's inverse is log base 3 of x. These are inverses. What if I give you g of x equals e to the x? Well, then the inverse, g inverse, is log base e of x. Although if you write log base e of x, you should be like, whoa, 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 that's not right. We don't write log base e. That's silly notation. So I'm going to take the log base e out and just write it as ln x, which really means log base e. But that's the notation that we prefer, is ln x. Well, what if I give you h of x equals log base 6 of x? I want you to be able to find the inverse of a log function very quickly, just as easily as you found the inverse of an exponential. So h inverse of x, because my base b is 6, my base of my exponential is also going to be 6. So 6 to the x. Notice your bases are the same in all of the problems. Even on g of x, where you didn't even write the base b there, it still is the same base. Lastly, I have p of x equals log x. Notice there is no base here either. What's his inverse? Well, I know the inverse of a log function is an exponential, and the exponential's base is 10 because it's a common log base. So my inverse is 10 to the x. I would like you to be able to do this very, very quickly because we will be using exponentials to graph logarithmic functions. So look at my red function f of x equals 2 to the x. you already know how to graph this exponential function because we've talked about it in the previous section. In the previous section we said we really only need 3 points is sufficient, and also knowing that you have a horizontal asymptote at y equals 0. This is enough information to get you the graph. So if I plug in -1, that gets me 1/2. I always have a 0, 1, and 2 to the 1 is 2. Again, those are before transformations. I think I'm going to go ahead and get 2 more points just for accuracy on this problem. Although these are my 3 key points, I just want to make it a little bit more clear when we have the picture why these are inverses. F of x equals 2 to the x, and I'm plugging in -2. 2 to the -2 is a 4th, and 2 to the 2 is 4. So let's go ahead and use this information with its horizontal asymptote, which we already covered in a previous section, to sketch the exponential function. I can go one more, 3. 2 cubed is 8. So this is getting me a very good picture with a horizontal asymptote on the x-axis, y equals 0. Now we already talked about if I have f of x equals 2 to the x base 2, I know his inverse is log base 2 of x. In fact, I'm going to go ahead and just put a f to the -1 here because we do know that these are inverses. We just talked about, I don't want you to have to do this algebraically every time. I need you to understand that 2 to the x exponential function and log base 2x are inverses. So I am trying to graph this inverse. Well, I could start picking x's here. So if I'm trying to plug in -2 into log base 2 of x, I have log base 2 of -2. And I'm trying to figure out 2 to the what equals -2. 2 times 2 times, how many times do I have to multiply 2 to get to -2? Well, if I keep multiplying 2 as many times as I can, I'm never going to get negative. This actually doesn't make any sense. I could use a calculator, but actually the calculator isn't able to do base 2. We'll talk a little bit about how to do this in the next section. But even if I was able to use the log button, log of a negative number gets me a non-real answer. It doesn't make any sense to the calculator. So at this point I'm like, I couldn't figure out what it was using my own brain. The calculator, even though I didn't use base 2, I just used base 10 in the calculator, still couldn't figure out what a log of a negative is. I don't think this method is going to work here. I can't just start picking any x's I want to plug into my log function. It was a good try, but we're unable to do that. I'm getting non-real answers and I'm getting stuck. So next we'd like to figure out another way we could do this. Well, I did put the red function here on purpose, the red exponential 2 to the x function. And I know that the red function is the inverse of the blue function. So what I'm going to do here, instead of trying to plug in values, is I'm going to use the fact that these are inverses to my advantage. And I know that whenever we have inverses, the x and the y switch places. So I'm just going to take the x values and put them into the y for my points, and I'm going to take the y values and put them into my x, or domain, for my points. So instead of the point -2, a fourth, I'm going to use the point a fourth, -2. Instead of the point -1, a half, I have the point a half, -1. Instead of the point 0, 1, I have 1, 0, 2, 1, 4, 2, 8, 3, all the way down. Notice that all of these x values are all positive. Whenever I plugged in anything into my exponential, I got out positive answers in my f of x. So therefore, when I switch around the x and the y, all of my domain are all positive. Let's see how this looks on the graph. If I plot 1/4, -2, 1/2, -1, 1, 0, 2, 1, 4, 2, and 8, 3, I have the sketch of log base 2 of x. When I connect these, notice what's happening here at the y-axis. These points on the domain are getting half as small as I go up my list. So if they continue to go half as small, half as small, half as small, I'm actually approaching the asymptote, which does make sense. My horizontal asymptote was the x-axis. So when I switch the x and the y, I have another asymptote. My asymptote is not going to be y equals 0 this time, or the x-axis. It's going to be x equals 0, or my y-axis, which is now not a horizontal asymptote, it's a vertical asymptote. So logarithmic functions are going to have vertical asymptotes. The parent ones are going to be on the y-axis, where exponentials have asymptotes on the horizontal x-axis. So now I have an image of log base 2 of x. Let's take a look at the domain and range of both of these red and blue functions. The domain of the red function is negative infinity to infinity. The range is from 0 to infinity. These are the same properties we talked about in the past section. The x-intercepts, well, remember there aren't any because it has an asymptote at the x-axis. The y-intercept is 0, 1. And the asymptote we've already talked about is y equals 0 or the x-axis. Let's look at the blue function, the logarithmic function. My domain is not all real numbers anymore. My domain can only be positive numbers. So we have 0 till infinity. You cannot take the log of 0 because we have an asymptote right there, so we have a parenthesis. My range, on the other hand, can go down forever and up forever, which is all reals. My x-intercept looks like it's at 1, 0. My y-intercept, well, there aren't any. And the reason there aren't any is because I have an asymptote at the y-axis, or x equals 0. So let's compare the properties of the exponential function with the properties of the logarithmic function. Notice my domain of my exponential is the same as the range for my logarithmic function, the inverse. And similarly, the range of the exponential is the same as the domain of the logarithmic function. Well, that makes sense because in inverses, the x and the y switch places. So that means the domain becomes the range and the range becomes the domain. This is exactly how an inverse works. Similarly, the x-intercept of my function is the same as the y-intercept of my inverse. And the y-intercept of my function and the x-intercept of my function aren't quite exactly the same. But if you think about the x and the y interchanging, the y-intercept of 0, 1 on my exponential function and my x-intercept of 1, 0, notice that the 1 and the 0 had to change places because we switched the x and y. And how come? Yeah, because they're inverses. So this is all falling together here with the fact that they're inverses and we have all the properties interchanging places. Lastly, I had a horizontal asymptote at y equals 0. When I switch the x and the y, I get a vertical asymptote at x equals 0. Just like when we studied the exponential graphs, the domain, range, x-intercept, y-intercepts, and asymptotes were all the same for all parent functions, f of x equals b to the x. Similarly, in logarithmic graphs, for the function log base any b of x, you will have the same domain. Your domain will always be from 0 to infinity. You cannot ever take the log of a negative. The range will always be a negative infinity to positive infinity. You can get all of the values for f of x whenever you plug in positive values for x in the domain. The x-intercept will always be 1, 0. You'll never have a y-intercept, and your asymptote will always be the y-axis at x equals 0. Again, this is all before transformation. When you transform, sometimes your asymptote changes, your x-intercepts will change, and sometimes your domain will change as well. So before transformations, the parent function, these properties all stay intact. Next, we're going to talk about transformations of functions in the next video.